So at this point, I'd like to invite participants to start sending in questions, and I'll start answering them. The first question that we have is, how does TrueAllele figure out the decay factor of each contributor if the computer isn't told what genotypes are supposed to be in there? Well, the computer solves this in a Bayesian inference. It just looks at the data and computes likelihood functions for different possibilities of the decay parameter, mixture weights, genotypes, and so on, trying to explain the data, and using Bayes' theorem, works out the posterior distribution. It's working out what the genotypes are from trying out different possibilities. It doesn't need to be told anything. It's trying out thousands or tens of thousands of different genotype possibilities and combinations, and considering them together with the decay factors of each of the contributors and many other variables in order to determine and sample from the posterior probability distribution of all the variables, and then pull out the decay factor as one of those variables. A second question is, does TrueAllele use all the data when it separates degraded contributors, even peaks from shared alleles and stutter? Yes, it does. TrueAllele always uses all the data. It doesn't use information buried in the background noise down at 5 or 10 RFU unless you ask it to. But it always uses all the data, and it works out with pattern comparisons of proposed genotypes and other variables, including stutter, against the data to determine which genotypes, stutter values, and degradation parameters are more probable than others. It works out the probability distribution. It wouldn't be able to use shared alleles if it were told, because it's not told what those alleles would be. So if you try to tell it that here are all the different genotypes and how do they account for shared alleles, that's not how TrueAllele thinks. If it's accounting for shared alleles, it's because it's trying out different allele pair possibilities that happen to add up and be at the same location and stack on each other. So it does use all the data in separating degraded contributors. The third question is, does turning on the degraded DNA option make much of a difference to the final match statistic? And sometimes it can, like we saw, it had an impact on one locus here, helping to resolve a question about stutter. But in general, usually the impact would be about 1 or 2 log units, 1 or 2 ban, and it doesn't make that much of a difference to the results. The next question is, how can TrueAllele account for allele dropout without knowing the suspect's genotype? It's true that there are methods of allele dropout that need to know the suspect's genotype in order to figure out dropout parameters and other parameters. But TrueAllele simply determines the probability distributions for each of the contributor genotypes, separating a mixture out into those different genotypes and their probability distributions at each locus. It doesn't know the suspect's genotype. It doesn't care what it is. It'll start from the data to do the separation, and then whatever it finds, whatever best explains the data, will then be compared. And if there is dropout, the result may be a loss of match statistic at the loci where the dropout was most influential. The next question is, why doesn't dropout software properly handle dropout artifacts? The answer really is that just putting in a dropout parameter isn't going to handle dropout artifacts, or at least not well. Dropout software often has a threshold, so the quantitative DNA is reduced to all or none events. It's not accounting for peak patterns, and it's trying to add a second parameter, a dropout parameter, or maybe a third parameter, a drop-in parameter, to a threshold parameter, trying to explain a 100-dimensional problem with just a few parameters. That tends to not work. And the question is, regarding slide 12, why wouldn't the blue contributor degrade at the same rate? And the answer is because it doesn't a lot of the time. Different contributors may be subjected to different environments. They may be present on an article of clothing or on some substrate for different lengths of time and undergo different amounts of degradation. If the amount of degradation is pretty much the same, then accounting for degraded DNA is not going to have much of an impact at a particular locus. That's more of a preferential amplification issue. But when there is a different amount of degradation between the different contributors, which we do see, not half the time, but certainly more than 10% of the cases that we look at, then the computer can determine those differential rates of degradation. The next question is, why does a peak that doesn't exist in the electropherogram get any weight of probability as a possible contributor? So another way of looking at this, since TrueAllele is not looking to assign weights to peaks or alleles, but to allele pairs, is why would a genotype allele pair have any weight of probability if the peaks that might support it in the data aren't there? And the answer to that question I can show in this picture. If you look at the top, it's just Bayes' theorem. The posterior probability is proportional to the likelihood times the prior. On the right, in brown, every genotype has a prior probability. The likelihood is never exactly zero. There's always some small number, even if it's a very small probability. And so when you multiply a likelihood times a prior, you get a posterior. The likelihood ratio is kind of related to the posterior to prior probability. And so if the likelihood reduces the amount, maybe tenfold or 100-fold, because there's less data present that corresponds to that allele pair, then you'll get a reduction in probability, but that doesn't mean that it's not there. I guess another example that might be more intuitive would correspond to flipping coins. If you flip a coin, there's a prior probability as to what the chance of heads is, maybe 50-50, and you flip a coin 5 times and it comes up heads 5 times and tails no times. That doesn't mean that you now believe that the event must be heads with 100% probability. It means that the probability of its being a 50-50 coin has shifted maybe more towards a probability biased towards heads, but it doesn't make it 100%. That's the way probability works. It shifts the probability distributions. It doesn't put zeros in. The next question is, how do you decide when to invoke the degradation parameter? That is, when do you turn it on? We know it doesn't make that much of a difference, and so we often don't bother with it. But if we look at the data and we see that the peak heights seem to be changing in proportions and different patterns, we'll turn it on. If we're running the computer for a long period of time anyway, maybe 100,000 cycles, then there's no harm in turning it on. It's just doing more modeling. So we tend to do it when the data indicates that we should, based on the patterns or how complex the mixture is. The next question is, do you have a list of all the parameters TrueAllele models? And the answer is that list was shown in the part 1 of this talk on genotype modeling. The next question is, can TrueAllele similarly account for drop-in possibilities, especially as in low copy number samples? If so, can you summarize the data? TrueAllele accounts for drop-in in the same way that it accounts for drop-out. The patterns that it's proposing when compared against the data, if the genotype has an allele pair in it and that allele is not present in the data when it's supposed to be, or it's present in the data when it's not supposed to be, that will shift the probability distribution of that contributor's genotype at that locus to other allele pair possibilities. So when the data doesn't support an allele pair possibility, either because of alleles that aren't there, drop out, or alleles that aren't supposed to be there, like drop in, that diffuses the probability and will reduce the likelihood ratio at that locus. Drop in is not the most common event, and so affecting a locus or two tends to not have much of an impact on the overall DNA match statistic. In your example where the 7 dropped out, why would TrueAllele specifically propose allele pairs with a 7 but no other missing alleles? The answer is that it's proposing a lot of low-level probabilities. This is just an artifact of the display. Because the green bar has to be displayed, the 7 and the 13 as an allele pair would be displayed, along with that very low blue bar on the left. If you notice on the top right, we're only looking at this result at a 95% probability, because a 99% probability would bring in 10 or 20 other allele pairs. So those are all considered, but because we're specifically asking the computer what's happening at 713, a low probability event that ordinarily wouldn't be displayed is being displayed, and at a 95% level. And again, at a 99% level, we would see very many allele pairs, and they would include alleles other than 7, 12, and 13. The next question is, if the degraded DNA option doesn't change the final result much, why use it? That's a good question. And the answer is that sometimes it does. Most often it doesn't, but it can. And in situations when you may have a comparison to objectively inferred evidence genotypes that produces a match statistic in the hundreds or thousands without using the degraded option, and when it does make a difference, and now you're looking at a match statistic in the tens of thousands or hundreds of thousands by letting the computer do that extra work, that can make a difference in reporting on a match. Next question. Does including the decay/degradation factor significantly affect the time it takes to generate an answer? If so, would you recommend not using it if time is of the essence? It's a really good question. So several things here. First, the degradation decay factor doesn't affect the time that much, but because separating out decay curves is a known hard problem in science, it's something where we use it when we run longer Markov chains. We're more comfortable running the chains at 50,000 cycles than at 5,000 cycles. So while the factor itself doesn't significantly increase the time if you're running it longer anyway, it's not going to do very much if you're running shorter. So you do need to run it longer. It's also true that in studies that we and some of the user labs have done, that most of the time, maybe 95% of the time, you're done with the TrueAllele results on a mixture in a few hours, running maybe only 5,000 cycles. So I would have to say that most of the time you wouldn't bother with it on most of the data that you have, and you would just get results on your 2- and 3-person mixtures pretty quickly and leave it at that. But when there's an important case, and it falls in that 5% of cases that you just want to get more information on, typically for a minor contributor, say a handgun that has 4 people on it, it's all very low level and it's all kind of mixed together. If it's an important piece of evidence, it's an option that you have that lets you do more with what you have. The next question is it possible to present a webinar where we go through example cases? That's a great suggestion. It's not part of this series on how TrueAllele works, but it's something we'd be happy to do. Most of the talks that I give go through example cases, and we have a lot of those on our website. But if there's interest in our presenting example cases, people should email in that they want that, and we'll have sessions on that. We've also had requests to discuss our validation studies. We've published 6 of them so far, and talk about how to do validation, again, in a separate series. So if there's interest in that, please let us know by emailing Cybernetics that that's the sort of webinar you'd like to see. The next question is, PCR inhibition can cause many of the same artifacts as degraded DNA, but with different mechanisms. Will TrueAllele work as well in inhibited samples? The answer is yes. The data looks very similar in those circumstances. The next question is, in computing the decay factor, will TrueAllele provide error bars? TrueAllele does compute the uncertainty of all parameters, including the decay factors here, lambda 1 and lambda 2. So it's something that the system has and it knows, and it's something we could add to the interface. It's already determined and known. So it's a good idea, and if there's interest, which there seems to be, we can include that. Since, again, everything in TrueAllele is a probability distribution, including these lambda factors. The next question is, are RFU values in TrueAllele comparable to RFU values in GMIDX? The RFU values in TrueAllele are the RFU values that come from the .fsa files or from export files for GMIDX itself. So TrueAllele doesn't produce the RFU values, they're input that comes in. So since they're the same, I guess they are comparable. The question might be a different question, though. Let me think about it again. The question might be asking, is the modeling of the peaks in TrueAllele comparable to the modeling in GeneMapper? And the answer is yes. To that, we others, the Forensic Science Service 15 years ago, have done studies that shown that a regression comparison between the values is highly comparable. The next question is, what determines whether or not to increase cycle numbers in a mixture determination? Currently, we're doing it based on some rules that we have in our manuals based on our experience, and we're increasing cycle number based on genotype concordance and maybe the Markov chains and other sorts of concordance. So we'll follow protocols and run it on a first run maybe for 25,000 cycles and see what happens if we run it in duplicate. And if there's good genotype concordance, we can stop, and if there isn't, we'll continue. We're doing other work now to determine whether there are other ways that we can get good predictions of how many cycles to run. Okay, so I think that's all for today. Thank you very much for attending, and we look forward to seeing you on December 18th for part 3 of how TrueAllele works. Thank you very much.